I don't know why, what happened. This Akash Kumar, yeah, Akash got removed. Because of this recording, it got problem. So can you just text, anybody text Akash to rejoin? Okay. Can you view my screen?
Yes, sir.
All right. All right. So, so let me say about something which well, we have seen for second derivative, if it is greater than 0, then what happens? Convex downwards or upwards? Convex downwards, right? Yeah. And if the second derivative less than 0, then convex upwards. Now, if you did I remark it here about maximum in maximum? No. Yeah. See here. So f has continuous second derivative on AB and derivative double derivative at x naught greater than 0 for some x naught. Then the graph is convex downward at x equal to x naught. So remark here, maybe I should put this theorem. The same proof, almost same proof. What I want to change is the derivative less than 0. Your double derivative is less than 0. If a function f has continuous second derivative on AB and f double prime x naught less than 0 for some x naught belongs to AB, then then f is here it was convex downward. The graph of f is convex downward. In that case, would be in the graph of f the graph of f is convex upward. Right? Now the proof is at x naught. So which is at x naught. The proof similar to the previous theorem. Right? So, and this is an exercise to complete the proof. Analogously, you need to change the sign and you will get it. Same thing. Now, if we consider, I remarked last time also verbally, suppose f has continuous second derivative on AB, and for some x naught, f prime x naught is 0, and if double prime x naught is strictly negative, then f has a local max at x equal to x naught. Right? Is this fine? Is this fine? So the picture is so picture is something like this. See, we had in this case the picture is something like this. Right? In this case, this picture will be something like this. Consider this point and look at the tangent. Okay. It's something like this. Right? It is convex upwards. What was the definition of convex upward? Yeah.
The graph of the function lies below the tangent line at that point.
Right. So graph lies below the tangent line. So that's it. Now, this case, what will be the picture? Picture will be, see now here in this case tangent can be any line, right? But when f prime x naught equal to 0, what will be the tangent at x naught?
Parallel to x-axis.
So tangent will be parallel to x-axis. So suppose this is the tangent, and it will be, graph will be lying right down the tangent line, right? Which means at x equal to x naught is the point of maximum, right? So this is not a singular phenomenon. It actually comes from the behavior of the function, general behavior of the function. When you rotate this picture to make this straight line to be parallel to x-axis, it will be something like this. Yeah, is this clear? So similarly, remark 2, suppose,
Excuse me, sir.
yes,
So why do we need the continuity of second derivative? Why is just f dash x less than 0 in the range not enough?
that is, yeah, so if this takes, in this case, you are right. In this case, uh, the point is, see what we did, right? So that one, so continuity of the derivative is important, right? Isn't it? Because see here how we proved. So it is actually the continuity of the second derivative comes from here, right? So here you see, uh, you want, we have this one, if the double prime x naught greater than 0. Here, if double prime x naught is there, is x naught is not present, right? What is present is x naught plus theta times x minus x naught. So it will be some point around x naught, right? So if you look at the picture, x naught is there, and you are looking at point x. So this point will be somewhere here, somewhere here. So derivative, double derivative at this point is important, right? Near that point is important. Yeah, what you can say that that continuity at one point, that might be enough. Continuity at one point. So if it is near zero, then it will have the same sign. If that is true, then that is good enough. So what we had, you see, this is greater than zero, but what we need is actually this one. This one is greater than zero. X naught plus theta times x minus x naught. So if it were just x naught, then we would have one greater than zero at one point is good enough, right? Now here we are using the continuity to get this greater than zero. So that gives us this, all this greater than zero in this case, and of course less than zero will be given other case. So that is the reason we insisted on continuous second derivative, but I mean continuity around x naught is good enough. It's not, you don't need to, it does not need to be continuous on the whole interval. So continuity in a neighborhood of x naught is good enough. Or
Okay,
if
sir.
you
Thank you, sir.
assume, or if you assume this f double rest is x naught is less than zero for all x in neighborhood of x naught, that is also good enough. You see my point? So if you know this derivative is less than zero, not just x naught, in a small neighborhood of x naught, then also it's good enough. Okay. So most of the cases when you, I mean, when you did in school to find maximum minima, so most of the cases you actually do not bother about the derivative continuity of the derivatives, because all the problems which are given mostly infinite differentiable. So if it is thrice differentiable, the function is thrice differentiable on this one, then you don't need to bother about, I mean, continuity second continuous second derivative. Okay. So that will be automatically, second derivative will be automatically continuous. But in this proof, you need continuity in a neighborhood x naught.
Sir,
Yes.
so can you give an example where the second derivative is not continuous at x naught and this thing does not hold?
Well, you actually look at again this one. See the function. Yeah. So, so pathological examples. Most of the cases, your our old friend x square sine 1 by x will do r. Here also. So consider fx to be x cube sine 1 over x not equal to 0 and 0 when x equal to 0. Is it differentiable?
Yes.
Is it second time differentiable?
Mm-hmm. Yes.
Yeah, check this. If this is f is twice differentiable, but if double prime is not continuous, right? And f prime 0 will be 0, and here of course f double prime 0 will also be 0. But you can make it positive to just add by adding x square plus something. If you want, you can make positive, right? So in this case, both will be 0. So what kind of example you want? You want, I mean, it does not give the behavior. So here in this case, this will be 0. Now if you consider gx to be x square plus x cube sine 1 over x is not equal to 0, and 0 x equal to 0, g prime 0 is 0, g double prime 0 is 2. Let us check. So this example I have just constructed. I have not checked before. Let me check here. What is this function? So how is the behavior? Let me check. Let me see. Yeah, right. So it looks like, yeah, it has a minimum at this one. Right. Yeah. Yeah, that is true. It has no minimum. So what was your question? That
My question was if we do not take this assumption of f double dash being continuously differentiable. If being continuously second differentiable, then give a counter example such that this assumption is necessary to show that this assumption is necessary. But yes, it's done. Now it's
Yeah, no, 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 no. This assumption is not necessary. That is true. No, but there is a question here, right? So question is, so I mean, if you modify your question a little bit, then what you get is if suppose if you so one, I mean, if you want to try to find a counterexample of a function af, or example of a function af, where second derivative is not continuous, but I mean, second derivative is positive or negative, but f does not have, and then of course f prime x naught is 0, but still it doesn't have maximum or minimum, right? So think of this question. This question we have proved here assuming the continuous second derivative, right? So question is whether can you modify the proof. So I'm just asking question here. Your question modified a little bit in the context of this one. So can you, so is it true here maybe, can you relax the assumption of continuity of the second derivative in remark 1 which means whether can you relax the continuity of the second derivative and still get the result, or do you have a counter example where f doesn't have continuous second derivative at x naught, let's say, but f prime x naught is 0, f double prime x naught is less than 0, and but f does not have any local max. All right, so is this question clear? So question here, I mean, in this remark, can you relax the assumption of continuous second derivative? We have used in the proof here the continuity of the second derivative to get this derivative x naught is greater than 0 or less than 0. So that part perhaps is essential, but one need to give an argument. Whether this is true if you relax the continuity of the second derivative. Yeah, any other question? Okay, then let me state. Let me give the remark two. The remark two. Remark two is analogous to it. This one. Suppose f has continuous second derivative on AB and f prime x naught, and there exists x naught in AB such that f prime x naught is 0, f double prime x naught is greater than 0, then f has a local mean at x equal to x naught. So the picture is a convex function or convex downward, which is also called convex function, and one of tangent space parallel to x-axis. So it comes in this picture. All right. So this comes from the proof here. Convex downward, but when a prime x naught is equal to 0, then it will have minimum there, because the graph must lie above the tangent space, above the tangent line. This picture. Okay, so let me state. So when the first derivative non-zero, we know increasing decreasingness, and second derivative there would give you in which way it is bending, upwards or downwards. Now when the second derivative, when first derivative is 0, second derivative positive or negative, we get the maximum minimum there, and we know which way it is bending also. Now suppose second derivative also 0, then what happens? The next theorem is that if function f has continuous third derivative on AB, and there exists x naught such that f double prime x naught is 0 and f triple prime x naught is not equal to 0, then x equal to x naught is the point of inflection of the graph of f. See, when second derivative also 0, you go to the third derivative. Well, third derivative non-zero is always gives you a point of inflection. Well, if second derivative is non-zero, then there will be, effect of second and third derivative both, and second derivative will contribute there, and mostly it will be determined by the second derivative. Third derivative will not play that much role then. But when second derivative is 0, so first this third derivative will become non-zero, then it will be always a point of inflection. Yeah, let me ask you, can you guess why is that so?
Could you repeat that?
Yeah, so I've written this statement, right? Now,
Yes,
can
sir.
you guess why this is so? Why this is for secondary? Why if the second derivative is zero, third derivative is non-zero, it will always be a point.
Yes, the point is that here f double dash x naught is equal to 0.
Yes,
But if triple dash x naught is not equal to 0,
right.
which means that in the neighborhood of x naught, the double derivative changes its sign or its value. So because it changes, so the yeah, on one side it is less than 0, on the other side is greater than 0. So the concavity and convexity of the curve are different on both sides of x naught, and therefore we can call
Now,
it a point of
now,
inflection.
how do you know this double derivative changes? Yeah, that is true. Double derivative changes sign because this is non-zero. Yeah, yeah. So if you look at the Taylor series, Taylor's formula, x minus x cube will be present.
Yes, sir.
That's the reason it will actually be changing, right?
Yes, sir.
So depending on so double derivative will be changing because of that only. Changing will, is its sign because of that only.
Yes, sir.
So and that is actually the proof. That is actually the proof using Taylor's formula. So fx equal to x cube is the behavior of this function here at x equal to x naught. So mostly you see the polynomials, the behavior of the, I mean monomials generally are determining the functions locally in some way, right? And you might be wondering what happens to other derivatives, right? For suppose it is infinitely differentiable, or let's say n times differentiable, and what about the other derivative? How does they contribute, right? So suppose instead of it's just continuous up to third derivative, I say continuous up to nth derivative.
The
And
Taylor series basically says it all. Like if it's an odd derivative, then it changes sign. If it's an even derivative, then it doesn't. So
no, that is a different stuff. Suppose this third derivative is non-zero, second derivative is zero, and you don't know about other derivatives. But suppose it is differentiable, then how does this other derivatives, higher order derivative, contribute?
they don't contribute anything.
Yeah,
I
why?
mean, not anything significant. Because the first term, which is f triple dash, that is the third derivative,
Yeah.
that takes over. That changing sign is equivalent to the whole thing changing sign, because the even derivatives after this will not change sign, and the odd,
Hmm.
even if they change sign, it will be the same. It will be in the same way. They will not change sign in the other direction. They will change sign in the same direction.
No, the point is, see, if you look at Taylor series, you have x minus x naught to the power n, right? X minus x naught to the power n. So as you go near x naught, this x minus x naught to the power n becomes smaller and smaller. So that is the reason higher derivatives will not contribute. So it will be a small perturbation of what the first non-zero derivative would give you. Do you see the point? Yeah, I mean, what Sam said almost same, but why is that? The reason is the presence of x minus x naught power n in the other terms. Whatever it is, small, I mean, odd or even, but this is small, very small compared to the, let's say in this case, third derivative. All right. So let's look at the proof. The proof is very simple, of course. is that you see what's there. Yeah, Ayush, what happened? Did you join? Okay, anyway, so let's look at the proof. So, so assume for the time being, suppose f triple x naught triple derivative is greater than 0. Is greater than 0. Now we use Taylor's formula. Fx is fx naught at x equal to x naught plus f prime x naught x minus x naught plus remainder term Rx, where the second derivative vanishes, so it will come Rx come as third derivative x minus x naught power cube factorial 3 f triple prime x naught plus theta times x minus x naught for some theta lies in 0 and 1. Alright, now so we need to look at remainder term carefully. So which means here, so the continuity of f triple prime gives that f triple prime x naught plus theta times x minus x naught is greater than 0. Right? Now therefore, the sign of the remainder Rx depends on the term x minus x naught power cube. Right? Now this function x minus x cube changes sign from negative to positive as we pass through x naught from left to right. Right? So therefore, the remainder are changes its sign which means from negative to positive. This means fx, which is fx naught plus x minus x naught times f prime x naught plus rx will be less than fx naught x minus x naught f prime x naught on x naught minus delta to x naught for some delta greater than delta greater than, right? And if x will be greater than fx naught plus x minus x naught f prime x naught on x naught to x naught plus delta, right? So that gives, this implies x equal to x naught is the point of inflection for the graph of f. Okay, so let me state the final one, which I mean, depending on odd and even what people are saying, uh, how this, whether this is max mean or point of inflection, or how, whether it is convex upward or convex downward, depending on the derivative, higher order derivative. So let me state this one. Let f from AB to R be a function such that f double prime x naught is 0, which is equal to f n minus 1 derivative, all are 0, such that function such that this one, this second fn is continuous on AB and fn x naught is not equal to 0. For some x naught. So x naught is fixed in the very beginning, such that for x naught in AB, this one. Then 1, if n is even, then the graph of f is convex upward or downward, depending on f prime x naught greater than 0 or less than 0. Upward means, yeah, less than 0, and or sorry, or f and x naught greater than 0 respectively. So upward means this, depending on this, downward depending on this. If n is odd, then x naught is a point of inflection of the graph of it. All right. So moreover about maximum minima. So in addition to this, in addition to the above assumption, if we assume f prime x naught is 0, then the following holds. So this is a statement about same statement about maximum minima. So f prime x not equal to 0 means tangents become parallel to x-axis, and that is why you get the following. If n is even, then f attains max or mean depending on whether fn x naught less than 0 or fn x naught greater than 0. Right? So you can determine max mean if even if the second derivative is 0, you can go to the higher derivative and determine whether there is a maximum or mean. Second thing is if n is odd, well, then x naught is nothing changes. X naught is a point of inflection for the graph. So this statement you might have seen, right? So how many of you have seen these things? This have you seen? Maybe in school or first year. Yeah. Have you seen this statement before?
Yes, sir. Yes, sir.
And a proof?
Not the proof, but the statement.
Now you know the proof, right?
Yes.
Just using Taylor's formula. Yeah. So you have to use Taylor's formula. All the other derivatives 0. So after first derivative, another derivative will occur. And the same argument, whatever we have given here, would give the proof. Right? Yeah, so proof should be an exercise, easy exercise, because just same argument as we given for third derivative, second derivative and third derivative. And yes, yesterday somebody asked me whether this is some if and only condition are there, right? About this, about the behavior of the second derivative, every behavior of the function and the second derivative. So let me state this one and finish the class for today. Here, this will prove next time. So let f from AB to R be continuous and have continuous have second derivatives on This one. See, we have not assumed continuity of the second derivative, but we assume that every point, at every point, second derivative is there. Okay. Yeah. Then the graph of f is convex downwards, downward on AB if and only if double prime x greater than equal to 0 for all x in AB. I'm sure you have not seen this one, right? So this is an if and only if condition. So we have to assume this equality as well. So there might be, so the last time there was a picture, right? So there is a picture, something like, yeah, this one. So we have considered this one as well in this case. And you get a necessary sufficient condition. That you get a necessary and sufficient condition. All right, but what do you mean by convex downwards on a closed interval, right? So convex downward on AB. So f is means f is convex. So convex function we have defined on AB, that is for every point x1 comma x2 in AB, f of tx1 plus 1 minus t x2 is less or equal to t times fx1 plus 1 minus t f of x2 for all t in 0, 1. Alright. Actually, this is true for closed 0, 1 because when it is 0, you see this is x2. When it is 1, you see this is x1. And this side also. It will be the same. Alright. Okay, so we'll prove this one next time on Thursday. Sorry, on Friday. Yeah, any question?